Hi, everyone. Welcome to the Ockam community call for November 2021. Thank you all for joining. Our plan today is to talk about how Ockam enables end-to-end encrypted communication for any application, not just Rust applications, and how that's achieved using Ockam routing, inlets and outlets, and secure channels. We have Alexander today, who will present a deep dive into inlets and outlets. But before I hand it over to Alexander, I will do a brief overview and kind of set the problem for everyone. So let me pull up my screen. So Ockam is a mechanism to create, or a set of tools to create secure communication between distributed applications. And if you think about it, distributed applications kind of operate, any application kind of operates in this environment, right? There's the application in the middle. It's usually running in some kind of machine, could be a virtual machine, but it's a machine. That machine is operating in a network. That network is part of some kind of infrastructure. And then, of course, we have the internet outside of it. And all of these boundaries are places for us to do various types of checks, where we can ensure certain safety and security guarantees of data that our application is sending over the network or receiving over the network. Now, like I said, the type of machine that this application is running in could be all sorts of different types, right? Could be a virtual machine, a container, a Kubernetes pod, a rack server in a data center, an embedded device, like an IoT device at the edge or something like that. The network that machine is part of could also be all sorts of things. Could be a virtual private network in the cloud or VPC in AWS or something. Could be a network in Kubernetes, could be a NAT in like a home network or a private data center. Could even be non-IP wireless protocols like LoRaWAN or Zigbee or something like that. Could be various types of industrial networking protocols. And then, of course, these networks could then be running in all sorts of different infrastructure, the cloud, a private data center, a edge data center, a home network, a hospital, a factory, etc. Regardless of all of these variables, we need to kind of think about the same security guarantees of messages or data that is being received by our application and data that is being sent out by our application over the network. But if we kind of zoom in a little bit or zoom out a little bit, actually really what's happening is there's the same network, but inside that network, there are lots of machines. And inside each machine, there are lots of different applications. And the application we may be writing may be this like tiny little blue box here, and we're trying to talk to this tiny little blue box in some other network somewhere else. And we're trying to exchange messages securely between A and B. That's really the operating environment of most applications. So, if you're running inside a home, there might be lots of different connected devices in the house and lots of applications in those houses, in those devices. If you're running in a factory, the number of the machines multiply. If you're in a data center, it multiplies even further, etc. But broadly speaking, this is what our operating environment looks like. And our goal is to enable secure communication between A in one private network and B in a different private network. And the traditional approach to do something like this sort of looks like this, right? There is, if your B here is a server of some kind, then what we do is, because we don't want to expose B directly to the internet and expose a port on the internet, because protecting the server B from the internet and all sorts of denial of service attacks and bots, etc., that may attack B from the internet, we don't want to expose B on the internet. So usually what we'll do is we'll expose some kind of intermediary, like a load balancer that is designed to withstand attacks from the internet. And we'll expose it, and we'll have a TLS server here to terminate TLS. And then A would make a client connection to something like TLS. And then from from that load balancing server, we would have a unprotected connection coming back to B. In some cases, this connection may also be protected, but regardless, this is sort of what our topology usually looks like, especially if B here is some kind of server, usually in the cloud. The problem with this approach is all of these other applications within the same network boundary could be compromised in some way. And our application server here, B, has no way of knowing and distinguishing traffic that came from the legitimate load balancing server, or it may come from a malicious, compromised little application here, because it was our test application. We didn't put in too much thought into securing it, and now suddenly B is compromised because the traffic from this test application and the traffic from our load balancer looks the same to B. So that's one kind of configuration usually we'll find, especially if you have servers, if B is a server and A is a client. Another configuration we may find might look something like this, where A and B are both clients, and the actual communication is happening between A and B, but because they're both clients, they don't want to expose anything on the onto the internet, and we use some kind of intermediary cloud service, and A makes a secure connection over TLS to that cloud service. B makes a secure connection over TLS to that cloud service. However, doing this in a way where A is authenticated and B is also authenticated can be hard. You have to think about things like mutual authentication in TLS, or come up with some other client authentication protocol. If you have lots of A's and B's in your application, think IoT devices or mobile devices, then you have to think about key management, certificate management at a very large scale. And even if you do all of that, your communication is completely vulnerable and exposed in this cloud environment, because if something goes wrong in this cloud environment, then because this guarantee between A and B's communication is not end-to-end, your traffic can be compromised, spoofed on, spied on, spoofed, etc. Right? So because these guarantees aren't end-to-end, the vulnerability surface of our application becomes very large. So these are kind of a few common ways applications are arranged. With Ockam, what you're able to do is create end-to-end trust between A and B through a bunch of intermediaries. We can do this in our earlier topology like this, where this can be an intermediary and Ockam's guarantees would be between A and B end-to-end. So this exposed server would just route data through. And we can do it even in this scenario where the cloud service is just routing data between A and B. And there is a whole video from our previous community call where we talked about how this works with Ockam routing, and I'll leave a link to that in the description of this video. So please check that out if you want to dig deeper and understand how this works. But the end result is that we can now, regardless of the topology, regardless of how many intermediary nodes are between application A and B, we can have end-to-end guarantees of data integrity, authenticity, and confidentiality between A and B. And this can't be compromised by compromising the network boundaries of any of these environments because A and B mutually authenticate each other and can know that the data that B receives could only have originated at A. So it's a simplified view of that might look like this, right? We have Alice, which is A program, and B, which is Bob, which is the B program, and you can have a cloud service in the middle and two transport layer connections over which we have end-to-end guarantees. And this is unique, right? The reason we can do this with Ockam is because in Ockam, the secure channel is decoupled from the transport layer. So you can have two underlying transport connections, but one end-to-end encrypted and mutually authenticated secure channel. But it doesn't stop there. You can have any number of underlying transport layer connections, but have one single end-to-end encrypted and mutually authenticated secure channel. So with that in hand, to do this, the Alice program and the Bob program have to be modified to use the Ockam programming library, which is available in Rust. And that's not always an option, right? So we're not always able to modify our program. This could be because our program is a legacy program. We don't have the ability to modify it, or maybe the program is provided by a third party. And so, or you just want to kind of get started without doing too much programming. In all of those scenarios, it would be nice if Alice and Bob could have secure communication with each other without modifying, without us having to modify the code of Alice and Bob. And this is where inlets and outlets come into the picture. So in that scenario, what happens is, let's take this little blue box over here. That blue box becomes our inlet, and this blue box becomes our outlet. Or so essentially, instead of modifying A and B, we place a sidecar program next to A and B that can facilitate secure communication between A and B without modifying the code of A and B. This is not as granular control as you can get with modifying the code of A and B, because if you modify the code of A and B, you can, or if you're writing A and B from scratch, you can make granular decisions based on various trust policies at the level of each message or each data item that you receive in A and B. Whereas if you run inlets and outlets next to A and B, then you can't make granular decisions about access control. You just are trusting data as a whole. So there's a trade-off here where you can get started quickly with inlets and outlets by running them next to your existing code and don't have to modify the code. But the trade-off is that you don't have as granular control on making trust decisions about individual data items that you're receiving over the wire. So that's the trade-off. I won't go into this picture. I'll let Alexander talk about how you can build and use inlets and outlets. And then after we've done that, towards the end, I might come back to this picture and give you a little bit more detailed view of how this works. Over to you.
Yeah. Thanks, Mrinal. Hello, everyone. So the plan for this community call is to go and live code one of our guides. So to start, this guide is available at our main Ockam repo under documentation, use cases, and to encrypt all application layer communication. And the things we'll do in this community call is like 99% identical to what you can find here. So we'll start with some very simple and kind of made up examples. And we iterate and we'll end up with something that is really close to a real world scenario. So this is a picture of how we want to start. In this case, we have some arbitrary client that want to talk to a server using HTTP over TCP. and we want to try Ockam inlets and outlets and see how the traffic can go through them. Okay, so to start, I have 4 bash windows, and let's run some simple server. So I will explain quickly what this does. We'll create some temporary directory. We'll go to this directory and run a simple HTTP server that will serve local files. But since we do not want to expose any files, we'll just serve empty directory, and I'll use port 5001 for this server. Okay, and just to test that this server works, we'll just run some GET request. Okay, so we got our response. We see that server saw our request and everything kind of works now. Then let's start with writing some code actually. So I have an empty project. There's only one dependency. This is Ockam, latest version of Ockam, and there's like empty lib.rs, and let's create some example. So in first example, we will run inlet and outlet in one node. So we only need one executable. I'll call it one inlet outlet. Okay. So let's start with a main function. So every Ockam program will have this asynchronous main function with our macro.
Sancho, could you make it a little bit bigger? Yeah. It's a little hard to read.
Yeah, sure. Okay, so instead of a regular main function, we'll have this asynchronous main function and use this proc macro, which will actually start the runtime for us, start our actor system, and like just prepare everything for us so we can start working. Let's import some dependencies. Actually, let's compile it. First, compilation kind of takes some time. Okay, actually this compilation error is predictable. We do not use context, and so let's just start doing something. So first of all, since we want to use TCP in our example, let's just start TCP using Ockam. Let's import that dependency from Ockam, and this context is kind of handle, and it allows us to work with the actor system, and you will see a lot of Ockam calls will require passing reference to that context. Okay, so let's get back to our picture. We want to start an inlet and outlet. This is our like main function, our node. So, and usually we want to start outlet first because outlet is kind of a server and inlet is kind of a client, and obviously you need to start server first, right? So let's just see what we have in our TCP object. So we want to create outlet. There's create outlet function. There's address at which it will be accessible. Let's just call it outlet. And there's a TCP address at which it will be listening for incoming connection. And in this case, it can be just, let's call it 4001, right? And this function will return to us. Okay,
Sanjay, I think
this
needs to connect to 5001, right?
Okay, let's see. Let's just start writing and debug the errors. So that it will be funny, I think. Okay, and we need to also create inlet. So let's see what it asks us for. There's bind address. Okay, so yeah, you were right. This is the address we'll be listening for. And that's why here will be, this is the address of our server. And in this case, I'm using port 5001. Okay. And here we want to pass the route to this outlet. And let's just use route macro. And since both inlet and outlet are in our like one node, so this is very like simple route. It's just out, right? And this returns address of the outlet, of the inlet, sorry. Let's build it. I'm not sure we need this inlet address. Let's just ignore it. And let's actually try running this example. I'll use console for that. So it's cargo run example. Okay, I hope it's working. Let's now try to run the same GET request, but now we'll try to use port 4001, which is inlet port. And okay, actually it's working, and it's working like exactly the same as we were querying the server itself. But now HTTP traffic goes through our Ockam node. There's actually two different TCP connections, but neither client nor server knows about that.
Yeah, let's elaborate on that a little bit more, right? So the client and server, the client here is curl, the server is a HTTP server in Python. Neither of those were modified. However, what we did is instead of telling the client to send messages directly to 5001, we told it to send messages to port 4001 instead. And the inlet took whatever came on port 4001, wrapped it in Ockam routing messages. And because we told the inlet that it should send its messages to this route, which was a single hop to the outlet address, it delivered the message over to the outlet. The outlet unwrapped Ockam routing information and was left with a plain HTTP packet, which it then sent over to the server. So as far as the HTTP server is concerned, it received a regular HTTP packet from something that could reach port 5001 locally. So now we've got a client and a server that are talking through Ockam. And now in further examples, we'll see how we can make this communication through Ockam more elaborate and have various cryptographic guarantees. Go ahead, Sanjay.
Yeah, and to add to that, we not only did not modify client to server, we even did not restart the server. Yeah, so let's go to the second example. In this case, we're getting a little bit closer to the picture that Minal showed to us, is when we have two different sidecar programs and they are located on different machines, but those machines are accessible from each other within a single TCP hub. So I'm just gonna create a program for this inlet and for outlet. And to start, I will just copy paste this code and further modify it. Okay, so what exactly changed here? Actually, so this outlet is located here, and the only difference I think here is that this node should expose some port, in this case port 4000, so this node could actually reach to this node, right? So let's just listen on this port. The address is localhost. And I believe this is the only change we need on this side. Oh, actually, and we're not creating inlet here, right? We only have outlet on this node, while on inlet node, we obviously do not need outlet. And the only difference here is that if previously the route was very simple because it was on the same node, let's just move it to the separate variable. But now this outlet is located on another node. So the route this outlet will be, we will start with the address to that other node, and then it will be outlet inside that node. And the address here, TCP localhost port 4000. And let's import this variable and let's try to build it. Okay, somehow I removed the letter. Okay. There's one unused import, and that's all. So let's actually try it. So let's run outlet on this window. Let's run inlet on this window. Okay, and let's run our curl. Okay, and still works. Great news. We see a request here, response there. Renal, you want to add something?
Yeah, sure. You know, just to sort of so everyone's with us. This time around, what we did is we broke the inlet and outlet into two different programs, and the inlet was still listening on port 4001. So an HTTP packet from client, our curl request came to the inlet. The inlet wrapped it in an Ockam routing message. But this time around, we told the inlet that the outlet is actually one TCP hop away. So the inlet wrapped the HTTP packet into an Ockam routing message and sent it down TCP to the second Ockam node, which has the outlet. To do that, it created the TCP transport of Ockam created an outgoing TCP connection to port 4000. The message arrived at the outlet node. The outlet node then sent it to the outlet worker or actor. That outlet worker looked at the message and unwrapped all the routing information and was left with the raw HTTP packet, which is then just simply forwarded to our plain old HTTP server. So once again, the client and server didn't know that this message is traveling over 3 TCP connections. So as far as they're concerned, this message just arrived from client to server. But we were able to route it over a complex route, which would be useful as we build on this a little bit further in the next example.
Yeah. Also, I wanted to add something about the life cycle of connections. So this connection and this connection actually acts like one connection, and client and server doesn't know that there are multiple connections in between. And the lifetime of this connection is exactly as you would expect without anything in between. So every time we do a GET request using curl, there's a new connection that created here and here. As long as like at the point when the request is finished, those two connections, they just closed. But this connection is created once and it lives as long as those two nodes is living. Okay, let's go further a little bit closer to real world scenario. So the whole idea of Ockam is to enable authentication and encryption for data transfer. So let's just use the same example, but let's encrypt this connection. And in this example, we keep those two nodes on one machine, but in real world, they will be placed on different machines and use real TCP connections. We're just using one machine and loopback connection. But it would look like exactly the same, just the transport address would be different. Okay, so let's create example number 3. For inlet, I will just copy inlet code from example number 2. And for outlet, let's copy paste code from outlet number 2. Okay, so here it starts to get like a little bit more difficult. In order to create an authenticated and encrypted channel, we first of all need to create vault. Vault is a Ockam abstraction that is responsible for all the interactions with cryptography, for storing secrets, providing signatures, Diffie-Hellman, and all the required operations. Then we create another object called entity. Entity is responsible for representing some user with a set of public and private keys. And it's like something that you can talk to and authenticate this person, like assign some credentials to it and things like that. And then we want to create secure channel, and secure channel looks kind of similar to TLS or some other encrypted channel that you would expect. And in this case, the outlet node should create a listener that will listen for incoming connection, and inlet node will initiate the connection and the key exchange. So let's create secure channel listener on this side. Let's start it at address secure channel listener. And also secure channel listener accepts trust policy. This is a little bit off topic of today's community call, but a quick overview is there are different trust policies depending on how trust is built in your app. For this example, we just use trust everyone policy, which means that this listener will accept any incoming connection and negotiate the common secret. And you will have secure connections with anyone who wants to initiate it, right? Okay, I think it's done for the outlet. For inlet side, we obviously need the same vote and entity. But here we want to initiate secure channel. So let's go create secure channel. We need a route. So let's use variable secure channel route. This listener is located on the other node that is on that TCP address, and I remember we gave it this address, right? And let's use the same trust policy. This function will give us an address. This is the address that you send messages to when you want to use the secure channel. So every message that gets to this address will be encrypted and sent to the other side. So if you want to access outlet on the other side, we want to use secure channel. And this way we will reach the other node, and on the other node, the address is outlet for our outlet. Right, let's try to compile it.
Let's call that variable on line number 10 channel.
Yeah, sure. Still compiles after that change. Okay, let's try to run it. I shut down our example number 2. Outlet, what's one inlet? Okay, so here we immediately see there's some new information in the log. So here on the outlet side, we see that there was secure channel listener started, and actually this new secure channel happened here. And we can see that those workers were started at some addresses, and we can see that we verified secure channel, and we checked our trust policy rules, which were actually empty, for example, just for simplicity, and the same on the initiator side. So let's actually try to run our GET request again. Okay, and still works. So back to the picture, there was new connection here. Then we use these TCP connections. We run encrypted, authenticated secure channel using this connection. So this curl request was totally like fully encrypted. And if there was some man in the middle, passive or active adversary, they couldn't do anything with it, decrypt it or modify it without this side noticing that. And then on this side, we just decrypted everything and run regular HTTP request here. So if this node and client are located on one machine and this node and server located on another machine, so this is a loopback connection. So we actually don't care if it's not encrypted. And here there may be completely exposed TCP connections, but we encrypt it with Ockam.
Yeah, so we now have secure communication between our two Ockam nodes. And because the two nodes are sitting next to our two programs, we didn't want to modify the client and server. we can sort of assume that there the guarantees provided by the sidecar translate to the guarantees of the client because they're operating in the same sort of security context, right? You can imagine that these are the client and inlet node are on the same machine, and the server and outlet node are on the same machine, and there is a arbitrarily complex Ockam route in the middle over which we've established this secure channel. In this example, it went over one TCP connection, but we'll soon see it go over multiple hops. And so as soon as the HTTP packet leaves that machine on which the inlet and client are running, it is now protected from any kind of tampering, snooping, etc. Right.
Okay, and let's go to our last example. So this is really close to real world scenario because there are like two client and server may be located on networks, and you do not have direct access from one network to another network, and you need something in between that is capable of exposing TCP ports. And in this case, we will use Ockam Hub, which has a deployed Ockam node for everybody to use. And it will forward out our messages, but unlike TLS, we won't terminate our secure connection and it will go all the way through. So let's get to writing some code. Again, I will just copy what we already had. Okay, so the question is here, how would we actually access this outlet node from our inlet node? So in this case, because this is a server and usually server exposes some TCP port, but we want to avoid that. Instead, Ockam Hub allows us to create some forwarding address. So this node will connect to Ockam Hub and ask it for a forwarder address. And therefore, this address will be used for inlet node to get this transport access. So what outlet actually needs to do is there's a functionality called, so we don't listen on any ports and we cannot do that. We're inside the net. So there's a remote forwarder and we can create some address. So there is address of our Ockam Hub. We can connect to it using TCP, and the address is 1.node.ockam.network, and the port is 4000. We also need to specify a local address, the destination of the mailbox. So because we want to use secure channel, we'll direct messages from this mailbox to secure channel listener, right? Okay. So this will give us some string that inlet node need to know in order to access this node. So let's just print it. Okay. I hope that's all what we need to do here. Let's switch to the inlet. So In inlet, there's again a change in the route. So we want to create a secure channel, but we do not have a direct TCP connection to our outlet route. So instead, we want to connect using the same Ockam node. And instead of secure channel listener, we will now have some forwarder address. So the question is, we need to get forwarder address from outlet to the inlet. We printed it out in outlet. Let's just pass it as environment variable. So okay, let's try to compile it. Okay, it's compiling. Let's try to run it. So we again first start outlet. Okay, so we got our remote forwarder address. Let's try to pass it to our inlet. Okay, and again, we see that there's secure channel that was started. So coming back to the picture, we already have this connection, and we have secure channel going all the way from here to here. And again, to client and server, it looks exactly the same as in all the previous examples. So I expect if I run curl request again, it sort of works exactly the same. You know?
Okay, so so this is exciting, right? So what just happened is we have the client curl running in our local laptop, and we also have the HTTP server running in the same laptop, but it actually could be running in a completely different remote private network. Like, it could be my machine and your machine, or a machine in a factory and a different machine in a private data center, or a machine in a connected, or like a program in a connected car, and a server in a cloud VPC. Any of those combinations could have existed, where you've got two programs, a client and a server, running in different private networks, and they want to have secure communication with each other without exposing any open ports from those private networks. So they want to do it through the internet. And to facilitate it in Ockam Hub, we provide this as a service. So there is a routing service that allows you to create these forwarding addresses that can facilitate routing information, but can route encrypted data, right? So you don't have to decrypt your data and break the security guarantees of messages en route. The messages are delivered in a secure way, end to end, from that first inlet node to that outlet node. And in this example, we have two TCP connections along the path, but this could be any number of TCP connections. So we had a client that sent a HTTP packet in this case, which goes over TCP to port 4001. The inlet received that packet, wrapped it in Ockam routing protocol messages. That message then arrived at the secure channel, the beginning of the secure channel, got encrypted, and then once again got routed through to the node in Ockam Hub, where it arrived at the forwarding address. The forwarding worker at that forwarding address was told that any message you receive should be forwarded to this other Ockam node that is available using this pre-registered route. So it also then forwarded that message down to the other TCP connection through the other TCP connection that the outlet node had created. And the message arrived at that other machine, which was in a different private network. And now the outlet receives, the secure channel listener receives the message, it decrypts it, and now you've got a raw Ockam routing message. The Ockam routing message arrives at the TCP outlet, which unwraps all the routing information, and out comes a raw HTTP packet, which it then sends over TCP to our HTTP server. So to the HTTP server, it looks like I just received a HTTP request from something that could reach localhost port 5001. But really what happened is that our message left the local network, went through the cloud, came back into a different local network, and remained end-to-end encrypted throughout this journey. So yeah, that worked. Thanks a lot, Sanjay. All right, so to kind of conclude this this journey we were just on, we just looked at this picture, right? But what's unique about this picture is that this inlet and this outlet pair were a TCP inlet and a TCP outlet. However, it doesn't have to be just a TCP inlet. That's the example we just wrote. But in Ockam, transport protocols are pluggable. So you could just as easily have a Bluetooth inlet and a Bluetooth outlet if you wanted to, or a Bluetooth inlet and a TCP outlet if you wanted to. As long as we implement these inlet outlet pairs in the right way, we can achieve tunneling of arbitrary client-server communication protocols through any number of transport layer hops and still achieve end-to-end guarantees of data integrity and authenticity, which means that regardless of what your topology looks like, whether it has any number of intermediary nodes, maybe in different IoT scenarios, or if you're running intermediary services like Kafka or Confluent Cloud in the middle, any number of intermediaries, you can have end-to-end encrypted communication and mutually authenticated communication between these two programs in two different private networks without massively increasing the vulnerability surface of your application. All of these other programs in the same network could get compromised, but they wouldn't be able to compromise your application because your application trusts authenticated messages from on the other end. Similarly, all the programs here could get compromised, but they couldn't compromise your application other than maybe stopping the communication between Alice and Bob. But they couldn't inject new messages. They couldn't spoof a message or tamper a message or even spy on a message. None of that is allowed because the data integrity guarantees are end-to-end from here to here, which also includes a uniquely ordered nonce, so you can't inject messages that didn't originate from the sender of the message. All right, that concludes our presentation for today. Thank you everyone for joining, and see you next time.